Okay, yesterday we have seen about the effect of temperature and the effect of sediment concentration. So effect of temperature certainly I mean the property of the fluid, that is the coefficient of viscosity, is a direct function of temperature, and you know the properties of a fluid, I mean your fall velocity etc. is going to be some way or other related to the Reynolds number through your coefficient of drag, and hence the temperature has come into picture, which was explained yesterday. Okay. And similarly the effect of concentration also has been explained, and if the concentration is higher it is going to settle down, and the concentration can become higher when few particles cling on together, and this in terms of flux, then you can see that the fall velocity increases, and the practical relevance of this to the field of coastal engineering also I have explained yesterday. Now today we will talk about the effect of turbulence. Again, effect of turbulence, see where does this turbulence and all comes into picture. See, when you talk in terms of coastal engineering, the effect of turbulence is later I will also explain when I am talking about the mechanics of wave induced sediment transport. There you see that when the simplest thing is, when you look into the ocean you see that the waves break, right. When the waves break, what happens? There is a lot of turbulence created, and if you have a lot of turbulence you have a lot of mixing of the sediments. Okay. So this is one direct relevance, and when you have more mixing due to more turbulence, what will happen is the sorting of sediments will be more or less uniform, you understand. So this has a direct bearing on the quantity of sediments that are brought to the surface from the seabed. Now herein you have already seen how does the coefficient of drag vary when you have a Reynolds number and a CD. You see the curve something like this, right. So at low Reynolds number you see that there is a significant decrease in the coefficient of drag, and after a certain value of your Reynolds number you see that the CD is more or less constant, or more of the variation is not much significant. So now you have this in mind and try to understand the effect of turbulence. So the drag exerted by fluid on a body in a stream is directly proportional to the relative velocity at very small Reynolds number, that is, this is where you have the variation of the coefficient of drag. So one classification is where there is a variation of CD, and the other classification is where there is not much of variation of CD. So in the first classification, because of the variation in the CD as shown here, the random fluctuations in the velocity will not have much of effect on the mean drag. Hence we can say that there will be no effect on the mean drag, which will remain proportional to the mean velocity. Okay. After all, it is the velocity which controls. On the other hand, in the region where you have approximately the CD is more or less uniform, that is particularly in the case of larger Reynolds number, drag is of course proportional to the square of the velocity of the flow. So under such circumstances what happens, the mean drag will no longer be proportional to the mean velocity in case the random fluctuations are present. So this is what it conveys, that is, this is more important when you consider the practical application. I told you already, and this effect of turbulence is quite difficult to work with. The turbulence it is not so easy to work with the turbulence, although there are some research work which is in progress in some of the leading laboratories trying in order to understand the effect of turbulence. Now we move on to another important aspect, which is nothing but the permeability. Permeability, so there you ask, no, how permeable is this medium? Is this medium permeable? Is this medium permeable? No. So if you pour some water, it stands there, it does not penetrate. So this is defined as the state or quality of a material, or it may be a membrane, both has direct application in the field of coastal engineering, both the material as well as membrane. In fact, membrane has a wider application recently. So this is a recent a kind of innovation we could say, that at least for the last decade they are using these membranes for coastal protection. That causes, what does it do? It causes it to, that the membrane causes it to allow liquids. We are not interested right now in gases, at least liquids, to pass through it. If we want to keep things dry, then normally what do? You wrap it with a material with no permeability or very less permeability. So all of us know, because for non civil engineers I think even they must have been exposed to what is meant by permeability. But where does it find its application? For example, when you look at several structures in the coastal zone, why in the coastal zone, even in, for that matter, even the your highways, bridges, etc., or revetments for that matter. What will happen is, suppose for example I want to protect an area which is getting eroded. This is maybe this is a coastal highway, and the whole thing is probably initially the beach slope would have been something like this, and slowly as time propagated, then you see that the erosion has taken place. So the usual thing is, how do you protect this? You will, the simplest way is to dump stones. What will happen if you dump stones? If you dump too big stones, then there will still be some amount of water escaping through, and that might create some problems. Okay. So you have to be careful while using the stones. Normally under this case what they do is they use smaller stones, okay, and then they have a bigger stones, so that the bigger stones will resist the action, the forces due to the waves, and after resisting, the flow will take place, the flow through this medium will take place through smaller stones. So what will happen? The flow gets slowly dissipated. Is that clear? So that is the reason we have larger size stones, then smaller size stones, and then you have something like a filter layer. So the concept, again I am telling you, this is only to reduce the flow through the medium, so that this part is protected. Okay. Now that is how you consider the porosity or the permeability, etc., which we will be again seeing about the porosity and permeability. Now next comes your membrane. What exactly is this membrane? One typical example is when you have an area which needs to be protected, a beach for example. The beach is undergoing erosion, progressive erosion. How can we protect this? We use what is meant by geosynthetic material. This geosynthetic material, the purpose of the geosynthetic material is to allow the water to penetrate but retain the sand or the other materials. Okay. So what you can do is you will have the geosynthetic material here, wrap it, and then when over it you can have the stones or protection layer. Of course you need to have a smaller size stones which is called as a filter layer, and then over that you can have smaller stones. What it will do is when it brings some amount of sand to this area, the sand will be retained on the seaside and it will allow only the water. Okay. So there are varieties of geosynthetic materials available. The only problem is it is more favorable in location in non-tropical countries, because the material itself is a big again it is under discussion whether it can be widely adopted for tropical countries. Because what happens is when you talk about synthetic material, when it is exposed to alternate sunlight and it becomes wet and dry, what will happen? It become brittle after a few years. So once it becomes brittle, you know what happens, it breaks. So its effect is lost. So that is the reason people are still discussing about whether the geosynthetic material can be adopted. We will be discussing, we will be having a few lectures on the geosynthetics later. So you see that permeability or of a material as well as the membrane has some effect, significant effect in the design of coastal structures, and also when you talk about breakwaters, etc., which we will be looking at the design, classification, etc., later. Now coming to the permeability, there are different ways of expressing permeability. I have chosen this, that is the Darcy is referenced to a mixture of unit systems. A medium with a permeability of 1 Darcy permits a flow of 1 centimeter cube per second of a fluid with viscosity 1 megapascal second under a pressure gradient of 1 atmosphere per centimeter. So what are all the things you have, what are all the parameters you have? You have the rate of flow, you have the property of the fluid, that is the viscosity, and how does this fluid flow take place? This fluid flow takes place because of existence of certain pressure gradient. And how far it has to flow? It has to flow through a certain area. So you have the area, you have the rate of flow, cost, the rate of flow is induced by existence of a pressure gradient, and this is going to be done by a fluid with a certain viscosity. Okay. So this is how the permeability is defined, but for if you want to have more information you can read a number of books available. So now the most widely used formula for permeability, there are so this is after Fair and Hatch, which is widely used even today, and that gives as here capital K into G. So capital K is the coefficient of permeability. The coefficient of permeability is governed by this expression, wherein A is the package factor equal to 5, about 5, capital B, this is small b, but this is capital B, this is a Sand's-Shapes factor varying from about 6 for spherical grains to 7.7 for angular grains. We normally take an average also. And what is the other parameter? G is the gravitational constant. Now capital P is the percentage of sand held between two adjacent sieves, and DGM is your geometric mean of the mesh sizes of two sieves. I have already mentioned about the sieve analysis. Okay. So this is the diameter of the geometric mean of the mesh size of two sieves, and N is nothing but the porosity, that is the volume of voids in the sample of a sediments. You take a volume of sediments, then volume of voids in the sample of the sediment divided by total volume of the sand. I will not go into the details of how all these things are measured, etc. Okay. I suggest you refer to some basic books. Now herein you know how this permeability is calculated, what are all the parameters that are necessary. Okay. Now we we have more or less done with the basic properties of soil that are of direct relevance to coastal engineering. One important aspect is the liquefaction of sands. Liquefaction of sand is what? How important is liquefaction of sand? It is extremely important, because if you are going to construct a building in the location where you can anticipate the liquefaction, the entire thing is going to collapse. So when saturated sand is subjected to loading without drainage, so I have a container with sand, saturated sand, and this is subjected to loading. I have the load, okay. Now there will be pressure exerted in the pores. What will happen when the saturated sand is subjected to loading without any drainage, because it is now a confined container, what will happen? The pressure in the pore fluid may under certain circumstances approach equal to the total stress. What is total stress? Load by area, okay. So the pressure may equal to the stress. The total stress, that is sigma minus the pore pressure, is expressed or defined as effective stress. Under such a circumstance, when the pore pressure is equal to the total stress, then the effective stress must approach 0, right. Effective stress must approach 0. The shear strength and the deformation of soil are controlled by the effective stress. The shear strength of the soil, okay. As this approaches 0, the shear strength also become 0. What will happen? Can it withstand any structure, okay. So we should make sure that liquefaction should not occur. At this point, what happens? The sand becomes fluidized. The sand will now become something like a fluid. When it becomes a fluid, or when liquefaction occurs, the sand is unable to support any loads, and that will lead to total catastrophe. So, but I suggest some of you to read some extra books. Some of the books are a list of references are given at the end of my lecture material, where you can find apart from those references there are some other standard references where you can get details of liquefaction of sand, the physical the phenomena etc. in much more detail also you may be in a position to get. I suggest that those books for additional reading. So I will continue with the liquefaction of sand. So under continuous monotonic loading, sands will liquefy if the state of denseness is below a certain value. This occurs because loose sands during the shear tend to decrease in volume, but if drainage is prevented, the volume must remain constant, okay. So in such case what will happen? The applied stress is now transferred to pore water. When the applied stress is now transferred to the pore water, what will happen? This will result in an increase in pore water pressures and a decrease in the effective stress. So you do not want to have an increase in the pore water pressure, am I right? Okay. So on the other hand, now dense sands will dilate during shear, and this would result in a decrease in the pore water pressure, and liquefaction is not liable to occur. So the quality of sand, the characteristics of sand is extremely important. There has been a number of studies to understand the behavior of, I mean understand the variation of pore water pressures in case of rubble mount structures. What do you mean by rubble mount structure? We will be seeing about rubble mount structure in detail later. Now the kind of studies would be something like this. So you have some characteristics of sand, okay, and then you usually have a structure which is called as a breakwater. Again I have already emphasized the need for having the variation in the permeability of the structure. So you see that you have bigger stones on the top, I will emphasize about all this design etc. later. Now for this what is the usual kind of studies in relation to pore water pressures? Most of the studies are, so this will be extending like this, this is the, so you see that this is a structure which is called as a breakwater, constructed for creation of artificial harbors. And before you really construct all these things, you should understand about the pore water pressures, whether there is excess pore water pressures being built up etc. So you people have measured the pressures inside this medium as well as in the seabed, and these pore water pressures naturally have to be related to the characteristics of the waves, the characteristics of the structure as well as the soil. And this is one area which people are still working on, trying to establish relationships on the variation of pore water pressures as a function of the incident wave characteristics as well as the characteristics of the structure. So as we have seen that if you do not want to have your liquefaction, make sure that the pore water pressure is minimum, okay. Although it is quite easy in the laboratory to produce condition of zero drainage, yes of course it is very easy to create a condition of zero drainage, because if you have a tank, so there is no water which is released, right. So which allows the buildup of pore water pressures in loose sands. Sands will usually drain quite readily in the field, understood. So you have to be careful while you are doing some such studies in the laboratory also. If you are trying to do some test similar to something to do with liquefaction, you have to make sure about the boundary conditions. Two conditions under which this is not true, the above are when a sand body is encapsulated by pervious soils and when the external stress is applied so rapidly that would result in external, I mean pore water pressures, pore pressures, that the resulting pressures will not have an opportunity to dissipate the load that is being applied. So this is what I have been explaining with the help of some of the figures, and now if you want to have much more information on this, I suggest read the reference, that is the book written by Herbisch. So an excellent book giving all the details about whatever I have discussed. Now when I said about the dissipation rate, so I also, when I talked about dissipation, when I talked about the structure having larger stones, then followed by smaller stones, and then again by the smallest stones, that is progressive decrease in the permeability. The reason why I said is gradual dissipation, and gradual dissipation is always good. So, the dissipation rate is a function of sand's permeability, which is also a function of the state of denseness of sand and the length of the drainage path. Okay. So, the above discussion has clearly considered only monotonic loading. Okay. Then, but in the case of coastal engineering, we talk about cyclic loading. Okay. So, under cyclic loading, the soils will experience an increase in strain with each load application, because it is cyclic. So, all these things will, the strain will keep on increasing under every wave. Okay. So, in fact, when you want to test, you should test with a number of waves in order to understand the physics behind all these phenomena. I would like to continue that earthquakes are an important cyclic loading mechanism. For the earthquakes produce a number of shear stress reversals in such a short period of time, where it is a very short period of time, that the drainage may not occur even with rather permeable sands, and liquefaction can result. So, one is we are talking about the permeability of the sand. So, even if it is permeable, you can have the liquefaction to occur. Now, cyclic stresses produced by waves can also induce pore pressures in marine sediments, which is a well established fact. Okay. So, that is due to the action of ocean waves. So, the loading will be cyclic, and this will induce pore pressures in the marine sediments. So, you look at all the references given, and Herbisch was the one which I have been referring to. This gives a lot of information, not just on the characteristics of the sediments, but also on other aspects of coastal engineering, and there are other books also, and some of the other books which are given here are some books on the verifying the liquid limit or the plastic limit, the methods to conduct all these things, and the classifications, etc. And I have also given one or two publications on the results from pore water measurements, etc. Maybe it is of maybe although it is a bit old, you can still have some ideas. This is only to give you an idea about the nature of studies that could be carried out under the pore water pressures, etc. So, any questions under so with this we finish the sediment characteristics, and then we will go into the initiation of sediment motion or the wave deformation, etc. from next class. Okay.